is the second take of this video. So some of the notes are already there. You may just need to pause it, take the notes. But an equipotential surface, right, is one along which the gravitational potential is the same. This is just like we talked about equipotential surfaces in electricity with voltage. All right. So what that means is that this is a place along which a line along which no matter which point you chose along this line, if you brought a mass in from infinity, it would require the same amount of energy per mass to bring it to that point. So the point of this first exercise is to draw potential lines from the Earth's gravitational field near the surface of the Earth. Near the surface of the Earth, we'll assume the Earth is flat, for the place where we're considering, all right? And if we go up, the equipotential lines should be equally spaced apart. Okay? The next part asks us to draw the gravitational field lines. Since these equipotential lines are spaced equally apart, all right, the gravitational field should be uniform as well. Okay, approximately uniform near the surface of the Earth. The next exercise, all right, and I'll actually see it first. What do you notice about the relationship between the equipotential lines and the gravitational field? Well, the lines are perpendicular. Okay, the lines show the direction that the gravitational force would act. The field lines point in the direction of potential that increases in the negative direction. All right. So what that says is that the gravitational potential, all right, is going to become increasingly negative, all right, in the direction that the gravitational field lines point, going into that gravitational potential well, if you will. So next is to sketch the gravitational field around certain point masses. I'm not going to do that. I am, though, going to draw for you the equipotential lines, all right, around both of these. It looks something like this. It's from your textbook, all right? You can get pretty much the same thing. So if they're getting further and further apart, and at a certain point, all right, I'm going to have it just join up here like this. Okay, so those are going to be your equipotential lines around two masses, right? The amount of energy per mass needed to bring a point mass incrementally to that point. So when we're studying equipotential lines, okay, the change between them, all right, is a physically meaningful thing. So first of all, remember, in IV speed, slope is just gradient, all right? So the gravitational potential gradient is the gravitational field, all right, is the negative gradient of the gravitational potential with respect to the surface. All right. So I'll explain what that means here. The gravitational field is a negative gradient of the gravitational potential with respect to the surface. So what that means is that little g is equal to the change gravitational potential, negative delta V all over R. Right? Calculus is just slope, the derivative. Okay. So I mean that's pretty much just what you need to know. As you change gravitational potential relative to the position that you're in, you're going to be changing S V equal to your gravitational field strength. Right? We can average it between a couple of different positions. For the instantaneous, obviously, we'll be using the derivative. You would use the derivative, but we won't be doing that in this class. So, what is the average gravitational field strength between the two field lines, the equipotential lines, A and D, all right, in the diagram that you have there, if both A and D are 5 meters apart? Well, the change in potential between them, it does depend on which way you go, right? So we'll go from A to D, okay? When we go from A to D, right, that delta V is going to be negative 40, right? And then delta X is going to be equal to 5 meters, right? So what we end up with here is the gravitational field strength, the average gravitational field strength between the two of these is negative delta X. And this is negative delta V over delta X, which will give us 8. How much work would it take to move a 3 kilogram mass between them? Well, remember that work is equal to, go back to this other slide with the equations here. Okay, work is equal to actually coming. One of the other relationships we had is that delta V is equal to work done per mass, right? So if we want to solve for work, then we have a different delta V definition of delta V up here, right? We can say delta V is equal to negative G times that's R. We can substitute that in here, and we end up with work and multiply both sides by M. It's equal to M times G times delta R. Alright. When we solve for this, and it does say negative, but I'm going to drop the sign just because we're dealing with energy here, right? So it's just, if we're moving closer, we're removing energy, or doing negative work. So work on the system, that is equal to M times G times delta X. And actually, no, for right now, I will keep the sign, sorry, there we go. So it's negative there. All right, so it's negative 3 kilograms times 8 times 5 meters, negative 120 joules. Basically, it means we're moving energy from the system. All right? We're going to talk more about what negative work means when we get to the next chapter on thermodynamics. Positive work means we're adding energy to the system. Negative work means we're removing energy from the system. That's it. The graph shows the variation of gravitational potential V due to the Earth with distance r from the center of the Earth. How could the gravitational field strength of the Earth at any point be approximated from the graph? Okay? Well, take a minute, think about it. Gravitational field strength, we want it from this. What did I say before? I said it's negative delta V over delta X. Right? And this is, calculus. If you've seen this before, yay. If not, don't worry about it. It is going to be the derivative of the graph or instantaneous slope. Which, for those of you who haven't had calculus yet, you can draw like a tangent line, right, at any point, and then we can calculate, say that we want to figure that out there at like 13, 14, whatever I drew it, okay? That we would want to find out what the slope was at that point. We would draw a line tangent to that curve and find the slope of that line. When you get to calculus, it'll be a lovely day for you to understand what that true